Once again, hello. My name is Shpaner. Thank you for joining us again. I'm with UCLA Health. We're with UCLA Health, and we're excited to share our work on EquiBoots. It's a bias and fairness evaluation tool. It's a Python library, and we designed it to help researchers and practitioners measure and mitigate bias in machine learning models. So our goal is to bridge the gap between fairness research and practical implementation so that fairness isn't just an academic ideal, but something that we can actually operationalize in real world models. So at its core, EquiBoots is built to do four things really well. First and foremost, to identify biases in your model outputs. Second of all, to visualize them through clear and interpretable plots. Third, to bootstrap so that we can verify differences across many different samples. Fourth, to run statistical tests that quantify those disparities. And finally, to provide ways to adjust thresholds or decision boundaries to reduce inequity. What is bias? We hear all these buzzwords surrounding bias and fairness. Subgroups, vulnerability, disparity, parity, equity, and the list goes on and on and on. What we want to do today is simply demystify these terms. Bias and fairness are not abstract ideas, ladies and gentlemen. They're measurable and actionable. Our goal is to show how we can move beyond these buzzwords and actually evaluate those concepts in practice. So let's start with the fundamentals. What do we actually mean by bias and fairness? Bias in data occurs when the training set reflects existing social or structural inequalities. So for example, if healthcare data underrepresents certain populations, the models that are trained on that data will reproduce those same gaps. Algorithmic bias, on the other hand, happens when a model amplifies or creates unfair outcomes for different groups. So, in other words, machine learning doesn't exist in a vacuum, you see. It learns from the world as it is, not as it should be. So we may just want to blame the algorithm, sure, but as data scientists, it's paramount that we assess our models and check them for these biases before we put them into production. So what do you think in the audience? Welcome. What do you guys think? Do you think as people we're all biased? Let's get a show of hands here. Believe it or not, models are biased, people are biased. Bias exists, and it's important that we address it. And where does this matter in particular? Anywhere we see models making decisions that affect people directly, in healthcare, where we work, criminal justice, financial services, and so on and so forth. We've seen powerful examples of this in medicine, as a matter of fact. In one science paper by Obermeyer and colleagues, there was an algorithm that used to manage population health, and it said that it was less likely to recommend care for Black patients because it used cost as a proxy for need. And cost historically underserves marginalized groups. And in dermatology, another study, my gosh, found that models perform poorly on darker skin tones because most training data came from lighter skinned patients. Ladies and gentlemen, these are not isolated issues. They highlight how unrepresentative data directly leads to unequal care. So for all these examples, we use the adult income data set from the UCI machine learning repository because it has a wealth of information in terms of nominal data, numeric data. It's easy to implement what we want. And so we want to be able to recognize that bias can enter a model in two different ways. First, you have a biased model. So this means that the underlying algorithm or features themselves produce different outcomes by group. Second, you have a bias threshold, where the model might be fair in predictions, but the decision cutoffs applied downstream cause disparities. So for instance, using the same probability threshold for all groups may systematically favor one group over another if the base rates differ. So as you can see, there are many different types of biases, and we'll help you identify some of these. We're going to do something a little bit different here. Before we jump into the examples, here's a quick way to follow along. If you scan this QR code or go to the short link on the screen, it'll take you directly to our live tutorial notebook. You'll see the same examples we're talking through today, but everything from bias detection and model healing is there for you to open and view or bookmark for later. This way you can run the code yourself and explore how each fairness test actually works. I'll give everyone a minute here to scan the QR code. Cool. And so before we go straight into coding, we want to outline the different steps that we're going to be undertaking in this tutorial. First and foremost, we're going to define the reference group. This is the most populous group or groups that have bias in their favor. In our example with race, it's the white male. And then next, we split the data into slices and calculate the metrics. And lastly, we plot the metrics for comparison and conduct statistical tests to verify those differences. And I'm going to introduce my colleague Arthur to go over the rest of the tutorial.
Hello everyone, nice to meet you all. So I'm Arthur. I'm also a data scientist with UCLA Health, and me and Leon worked on this together. I'm going to be going through the coding portion of this presentation. So please feel free to follow along, as Leon said, in the collab notebook as we go. Before conducting any investigations with EquiBoots, you need to first have predictions and predicted probabilities from the model you want to test. Firstly, we need to define the two sensitive features we're going to be looking at, which in our case is race and sex. Then we create the fairness data frame. This data frame consists of the columns containing the variables we will be testing for bias. After defining our fairness data frame, we initialize the EquiBoots class, passing the true values, the probabilities, and predictions. After initializing the class, we call the grouper method using eq.grouper. You can see here we pass the sensitive features, the columns we want to analyze, sex and race, to the grouper method. After running this grouper method, you should get this feedback showing you the groups have been created. After grouping the data like we did in the last slide, we then need to slice it. We will use the slicer method from EquiBoots. Slicing cuts up the data, organizing it into the different subgroups so that we can do further analysis. Imagine taking a slice out of the pizza box and doing analysis on that slice of pizza. Once we have these slices, we can look at the metrics for each group. Using the getMetrics method, use the getMetrics method and pass the slice data. Here you can see it returns a dictionary containing the metrics for each of the different races, showing us the different performance metrics for Black people, Asian people, or for the other races in the data set. Now we have the metrics for each subgroup, we can do some analysis on these. Using the slices and the metrics we just calculated, we can start plotting the metrics by different groups. So you can see here, we saw this graph earlier. This is the RAC by race group. So use the EQ plot group curves method. This will allow you to plot the different graphs, including the area under the receiver operating characteristics curve, precision recall curves, and calibration curves. That's customized through the curve type variable. Looking at this graph, we can see that for the Black race group, the AURAC is higher than the others. For the Native American or Inuit group, it is marginally lower. While the AURAC is lower than the others for this group, we should exercise caution, as the counts are also much lower, thus affecting the reliability of this insight. We need another way of verifying differences, as sometimes simply looking at them is not enough. So in order to investigate these differences, we can run statistical tests. Firstly, we define the test config specifying chi-squared. This is the standard test type we use for point estimates. An adjustment can be applied if needed, and confidence level set depending on your preference. Then we pass this to the analyze statistical significance method. along with our metrics that we calculated earlier and the column name. This returns a dictionary containing the test results. You can see here this dictionary is not very easily readable, so we're going to be showing you how to present it in the next slide. So now that we have these statistical tests, we want to be able to visualize where we see a significant difference. We provide these tests to the plotting method EquiPlotMetrics forest. So this gives us a forest plot that highlights the test results. As you can see, there are two different types of tests, the omnibus test and the group test. The omnibus test compares the reference group, which in the case of race is the white group, against all the other groups. If a difference between a reference and any of the other groups is found, then we conduct individual tests. In this case, our group test found that there was a difference in precision for the Black and Native American subgroups, with the Black group having higher precision than the reference and the Native American group having lower precision. Okay, but maybe you want to verify these differences further. If so, you can use our bootstrapping functionality. Bootstrapping samples the data set with replacement, each draw being independent. Bootstrapping enables us to further verify the differences between the metrics by looking at them across many different samples. And our library EquiBoots makes this simple. When starting the bootstrapping process, we want to ensure that it is fully reproducible. Therefore, we need to create a seed list. This seed list is a list of integers, the length of your sample size. In our case, this will be the length of y test. To satisfy the conditions for the statistical test, we chose to sample a sufficiently large enough number of times. In this example, we have chosen 5001 to ensure we approach the normal distribution. We also sample across the whole data set and sample with stratification. Make sure when you're initializing to set the bootstrap flag to true. This turns on bootstrapping in EquiBoots and is the most important step when carrying out bootstrapping with our library. Now that we've initialized the class, the next steps are much the same as the point estimates. We want to group and then slice our variables. If you're following along on your laptop, here is where you may run into some issues. This grouping will take some time as we need to perform this action for all 5001 samples. We've sped this up here, but as you can see, it should take you, if you're running it on your laptops, at least a couple of minutes. And you're going to see a warning here, as we've chosen not to include the other race group, as this does not contain enough samples. This is a customizable threshold, which can be adjusted. So yeah, once it's finished running, you can call the slicer method the same way as we did for the point estimates, specifying the column name. Providing this data that we've just grouped, so the getMetrics method calculates the metrics across every sample. These metrics can be used in a number of ways, including looking at the disparities, or in our case, we're going to be looking at the differences. This difference is the difference in performance of the other subgroups against the reference group. So if we were to compare the white group with itself, we would see a difference of 0. We're going to see on the next slide what the results look like when we plot them. So yeah, provide these differences to the EquiGroupMetricsPlot method along with the metrics you want to analyze and the statistical tests. These are carried out in a similar fashion as they were for the point estimates. Looking at these plots, now we can see on the x-axis the different groups. So that is Asian Pacific Islanders, the Black group, and the Native American or Inuit group. And on the y-axis, we see the difference in the performance metrics. The 0 on this graph, and where you see that red dotted line, represents the reference group and is what we're comparing against. The further away the values are from this 0 line, the greater the difference is. And we can see that when we look across the different metrics for the Native American or Inuit subgroup, the model performs worse for ROC-AUC, average precision, and F1 score. The statistical tests have also found this to be significant, and you can see that with the stars. We can also see that the model performs better when we look at ROC-AUC and average precision for the Black race group, and this is also statistically significant. So now that we've identified some differences in the performance of our model in these different subgroups, we can have a look at starting to try and make the model more equitable through our form of model healing. So we're going to be finding different thresholds, different decision thresholds for the different subgroups. So using this method will help make the model's performance more equitable, and we'll deal with the bias threshold issue that we saw earlier in the slides. The find group thresholds method takes the data set, the probabilities, and the default threshold. This default threshold should be set as whatever whatever threshold your model is currently using. This doesn't have to be 0.5. Remember, this could be a threshold that was found to be optimal earlier across the whole data set, but it's not necessarily the best threshold for all the different subgroups. Once this method is run, it will provide you with these thresholds for each of the different subgroups, and you can see them here and how they compare to the reference group. So now we're going to be looking at what it looks like when we apply those thresholds that we found. So the two graphs on the left show the performance of the model using the default threshold. There is clearly some disparity when it comes to both precision and recall, with different subgroups performing better or worse than the reference group, shown by that red dotted line. I would like you to take note of how the recall is lower for all the subgroups. This can be seen on the graph in the top left, with all of the races scoring below the reference group line. If we look at the graph below, we see the precision. It is slightly higher for the black group and lower for the Native American or Inuit subgroups. However, now have a look at the right side. After applying the different thresholds we can see the recall is much more equitable, with all the performance metrics matching that of the reference group for all the different races. And you can see, have a look at how they're all lined up along that dotted line. If we go on to look at the precision, we can also see that it's equitable for the Black and Asian groups, but when we look at the Native American group, we can see the precision is actually slightly decreased. This is because although this form of healing can help find biased decision thresholds, we've already established earlier in the presentation that the Native American or Inuit subgroup performance is actually worse across all decision thresholds. Therefore, this form of model healing cannot bring the performance up to match it. So this is more than just a biased threshold and indicates to us further that we definitely have a biased model for this Native American or Inuit group. So as we get towards the end of our presentation, we'd like to outline a vision we have for the future. Equity is important, and as data scientists, we need to be conscious of what we put out into the world. It's paramount we strive to combat the biases we see in the modern world and not exacerbate them. We would like to see our tools used in production where they can make a real difference and hopefully identify biases in models before they have a chance to affect people. We also know that our step towards model healing is just that, it's a step, and it's still flawed. So that's why we're asking you today, if you have any ideas or suggestions or just want to be involved, to reach out and contribute and join us. We want to bridge this gap between research and practice with you guys involved.
And if I may add one quick comment, this is great, Arthur. Thank you so much. In terms of bringing transparency, some of you may be starting out in data science and learning the tools of the trade, if you will, and just looking at model performance as something as simple as accuracy, or, where we come from, it's more than that, right? We don't just, look at the false positives and the false negatives, right? If we build a model that tells a doctor a patient is going to live when they're going to die, we're not just introducing bias, we're introducing error, and we're making decisions that affect real data, that affect real people. So that's why this matters, not just in healthcare, like we mentioned earlier, in other industries as well. So you got to be careful about what your model performance is and how it's really being reported. Thank you.